In this section, we're going to look at applications of radian measure. In particular, I just want to make sure or emphasize that we understand this is an application of radian measure. All of the formulas that we see in this section are only valid if we measure our angle in radians. And so before we kind of start these problems, I'm just going to remind us what radians mean, where they come from, how we interpret this unit. We know it's a way to measure an angle, but we know, just to remind you, if we have a circle of radius 1, right, so if the radius there is 1, then the measure of an angle in radians is equal to the length of the arc that it cuts out. And we have another way to kind of interpret this as well. If I take a circle of any radius, so radius r, say it doesn't have to be a radius 1 anymore, then 1 radian is what I get if I take this length r, measure it up the side, so that's the same length here. That the angle that measures out is 1 radian. So radian, radius. It is innately and naturally tied to measuring length, which is why in a lot of applications we need our angles to be measured in radians. And in fact, our first application deals with arc length. So the length of an arc, which we denote as S, of a circle is proportional to the central angle, meaning, let's say I have a circle of radius r. If I measure this angle here, theta, in radians, the central angle, so from the center out, then that length S is just r times theta. Take your radius, multiply it by theta. We are actually already very familiar with a special case of this formula. If I took this angle and I went the whole way around, right, then the arc length would be the whole circumference. And in that case, the central angle is a full revolution, which is 2 pi radians. So circumference equals 2 pi r. We're already familiar. This is just a special case of this formula. Let's do a couple of examples. Here we're going to find the length of this arc shown. Now they gave us the angle, pi over 6. There's no units indicated, so it is understood to be in radians. If they gave us an angle in degrees, then we'd have to convert it, right? But whatever angle that they give us, we have to make sure that we have it in radians first. They tell us that the radius here is 3 inches. So this will be a fairly straightforward application of the formula. So S is equal to r theta, so we have 3 inches times pi over 6. Now you could write radians if you want, pi over 6 radians, but just understand that radians are dimensionless, so they do not contribute to units at the end of this calculation. The units that we get will be just inches. So 3 times pi over 6 is pi over 2 inches. There it is exactly, and we could approximate if we like. 1.57. All right, here's another one. It says a nautical mile is defined to be the length of the arc along a great circle of the earth for a central angle of 1 minute. It has been found to be 1,852 meters. And we want to know what is the measure of the Earth's radius from this information. So they gave us an arc length here, right? It says it's the length of arc, which is 1,852 meters, so that's S, along a great circle of the Earth. So a great circle of the Earth just means that it's a circle that goes around an equator, maybe not just the equator that we think of as kind of going through Central America or South America, I guess, but any circumference that goes through like an equator, like the largest kind of circle that we could draw around the Earth. and they've given us a central angle of 1 minute. So now let's just remember, it's maybe been a while since we measured angles this way. 1 minute, you'll remember back in the first semester of this course, one of the things we looked at was measuring angles in degrees, minutes, seconds. So a lot of the time, if we're using degrees, we use degrees in decimal form, like 30.5 degrees, right? 30 degrees and then a half a degree on top of that. But it's also common in certain areas to use minutes and seconds. So this is 30 degrees and 30 minutes. So you'll just recall that 1 degree has 60 minutes, 1 minute has 60 seconds. Okay, so the first thing we need to do, we want to find the value of r. We want the Earth's radius. We have the arc length. We need the angle in radians. Right now we know that it is 1 minute. So I'm going to take this 1 minute, I'm going to convert it to radians. There are 60 minutes to 1 degree. If I stopped here, I'd get degrees, but I don't want to stop here. I want to get to radians. And the equivalent to get to radians is that pi radians is 180 degrees. So I don't want degrees in my answer. I need to put the degrees on the bottom so that they'll cancel. It's equivalent to pi radians. Now I could see that the minutes cancel, the degrees cancel. I'm left with radians. And you could approximate this in the calculator, get it like a decimal, but I'm going to leave it as a fraction. So I'm going to pi over, and then 60 times 180 is 10,800. If you wanted to round this, like if you wanted to take pi and divide it by 10,800 in your calculator and approximate it, that's okay, but you want to make sure you don't round too coarsely. Take it out many spaces just to make sure that you have an accurate measure of the angle. So now I know theta is pi over 10,800. So if s is equal to r theta, and I want to find the radius, and all I'll do is divide both sides by theta. So that means that r is equal to s over theta, which is 1,852 meters divided by theta, pi over 10,800. I'm dividing by a fraction, so I'm going to multiply by the reciprocal. And I'll go ahead and get an approximation for this. Whoops, let's see. 1,852 times 10,800 divided by pi. 6,366,707. To the nearest meter. So we could leave it like that. Now, if you're doing a problem like this and you check your answer in the back of the book, they're likely to round this and just call it 6,367,000 meters, like rounding it to the nearest thousands. And the reason they're doing that is because in the measure that they gave us, there are 4 significant digits, and they were using 4 significant digits to give the result. It's okay with me, and more often than not, you'll probably see me take it out further than that, but that's why you'll see it rounded like this, a problem like this in the back of the book. All right, our next application is looking at the area of a sector. And if our angle theta is measured in radians, Then the area of a sector of a circle of radius r and central angle theta is given by this formula here, theta r squared over 2, where theta is in radians. So again, I'll just point out that we already know a special case of this formula. If the central angle, if it goes all the way around, right, then that sector is the entire circle, and the area in that case would be, let's see, if theta is 2 pi times r squared over 2, the 2's cancel and we get pi r squared. So this is a special case that we're already familiar with. Finding the area of a circle is pi r squared. This is a special case of the area of a sector formula. Alright, so we're going to do some examples here. So in the first example, in 211, they want us to find the area of a sector with central angle of 218 degrees and a radius equal to 5.25 inches. So they gave us the radius. We need that angle, however, to be in radians. So I'm going to take 218 degrees and convert it to radians. I'm going to do that by using the fact that they're 180 degrees in pi radians. So 218 times pi over 180 is 3.805 radians approximately. So that's what we'll use for theta. The area is theta r squared over 2. So that is 3.805 times 5.25 inches squared all over 2. Note that, radians are dimensionless, so they won't contribute to the units at all, and I'm squaring the 5.25 inches. So that'll give us square inches as units for a result, which makes sense for area. I'm going to turn to the calculator now. 3.805 times 5.25 squared divided by 2 is 52.44 square inches. Alright, let's do another one. Here they gave us the area, 75.5 square feet. We know the radius at 12.2 feet. We want to find the angle theta. So here's our formula, theta r squared over 2. And we want to find theta. So I think what I'll do is actually just some algebra first before I plug stuff in. I'm going to multiply both sides by 2 and divide both sides by r squared, and that will isolate the angle theta. So that gives us theta equals 2 times the area divided by r squared. And now for us, that is 2 times the area, which is 75.5 square feet, over the radius, which is 12.2 feet, the radius squared. So notice here, I'm just going to draw your attention to the fact that in the top I have 75.5 square feet, right? We're just squaring the feet. We're not squaring 75.5. In the bottom, I've got 12.2 feet all squared, right? These parentheses are important. In the bottom, I have square feet overall as a result, right? When we square 12.2 feet, we'll get so many square feet. So I've got square feet over square feet, which cancels entirely, giving us no units. That's okay, because radians are dimensionless. So when we work this out, we have 2 times 75.5. That's not being squared. And we're dividing it by 12.2 squared. Whoops, 12.2 squared. And I get 1.015, that rounds to a 5, radians. So the flip side to, when we use these formulas, and I was saying your angle theta has to be in radians, and even when they give us an angle in degrees like they did up here in the previous one, the first thing we had to do was convert it to radians in order for our formula to work. The flip side of that is if we're using a formula to solve for an angle theta, it is automatically in radians. All right, one more application to look at is angular velocity. So if I have an object moving in a circular path with constant speed, so imagine like a bicycle wheel just moving at the same kind of rotational speed. Then the angular velocity is the angle it passes through over time, and it's given in radians per unit time, and we denote it by omega. It looks like kind of a scripty W, but it's a Greek letter omega. V is the linear velocity, so kind of how fast something is moving on the edge. So if I think of a wheel spinning, let's say it starts here and then it ends up here, right? So how fast it's moving along the edge of the wheel is, that's V, that's the linear velocity. And it's in things like feet per second or centimeters per second or, kilometers per hour or something. And you compare that to this angle theta and how fast it's moving. And theta over unit time is omega. That's our angular velocity. So the angular velocity refers to kind of just how fast the angle is changing around. The linear velocity is really a measure of how fast something's moving around the edge of the circle. And these two quantities are related by this formula, V is equal to omega r. So the linear velocity is given by the angular velocity multiplied by the radius. So in example 213, they say that we've got a person on a hang glider moving in a horizontal circular arc of radius 90 meters with an angular velocity of 0.125 radians per second. So they gave us the radius at 90 meters. They gave us omega, and that's already the units that we need. That's radians per unit second. So this example is all ready to be done, and sort of plug the right values into this formula. V is equal to omega r, so that's 0.125 radians per second multiplied by 90 meters. Now we're going to perform this calculation. Let's think about the units for a second. We have radians, meters over seconds. Radians are dimensionless, so those units will disappear. And the result will be just meters per second, which makes sense because V is a linear velocity. So 0.125 times 90 is 11.25 meters per second. All right, let's try another one. A satellite maintains an altitude of 22,320 miles above a fixed point on the equator. That's going to be important. It says the radius of the Earth is 3,960 miles. What is the linear velocity of the satellite? So we want linear velocity. So we know that we're going to be using V equals omega r. We need r and we need omega. Now they gave us the radius of the Earth, but that's not going to be the radius that we need. Because the radius, in this case, we've got this satellite that maintains an altitude of 22,320 miles. So, if I imagine this to be the Earth, there's the center of the Earth, and here's the satellite, right? So this is the radius of the Earth, 3,960, and here is how far it is from the surface of the Earth, 22,320 miles. So the overall radius that we want is going to be the sum of these 2 points. So 22,320 plus 3,960 is 26,280. So we have our radius now, and that's miles. Next, what we need is the angular velocity. And here's where it's important that this satellite is maintaining an altitude above a fixed point on the equator. So if I know the angular velocity of the Earth revolving on its axis, then I'll know the angular velocity of that satellite. So the Earth revolves on its axis once, one full revolution every 24 hours. Of course, I need this in radians per unit time instead of revolutions, so I'm going to use the fact that one revolution is 2 pi radians. So the revolutions cancel. We end up with radians per hour, and then of course 2 goes into 24 12 times. So we have pi over 12 radians per hour. Okay, so next, now we're ready. We have our omega, we have our r, so V is equal to omega r, and that is pi over 12 radians per hour times 26,280 miles. Radians are dimensionless, so we will get, as a result, miles per hour, which makes sense for a linear velocity. Pi over 12 times 26,280. 6,880.09 miles per hour. All right, let's try one more. In the last example, we had to use what we knew about the Earth rotating on its axis, that it does a full, complete revolution every 24 hours. Sometimes they will actually give you omega, or give you the angular velocity using revolutions per unit time, which is okay, right? We know how to make that conversion. There are 2 pi radians to a revolution. Just be aware that when they abbreviate revolutions, they do so just using a lowercase r. So if you see r per min, or r per second, or r per hour, just know that that means revolutions and not radians. Radians will either have no units or will be abbreviated RAD. So just a plain old r, little r, is revolutions. In example 215, they tell us that the flywheel of a steam engine is 0.3 meters in diameter, and it's revolving at 420 revolutions per minute. And we want to know how fast a point on the rim is moving. So they're asking us for linear velocity. First things first, we'll just know that they gave us the diameter here and not the radius, so we're going to cut that in half. So the radius is 0.15 meters. And I'm going to just find the angular velocity real quick in radians. So 420 revolutions per minute times 1 revolution is equal to 2 pi radians. So these revolutions cancel. We've got radians per minute. 420 times 2 pi will be 840 pi radians per minute. There's our omega that we're going to use. So V is equal to omega r. This is 840 pi radians per minute times the radius, which is 0.15 meters. And again, you could probably predict what I'm going to say at this point. I'm going to remind us all that radians are dimensionless, so those units won't appear in our result. We're going to have meters per minute at the end, which is a linear velocity unit. That's what kind of units we would expect to get. 840 pi times 0.15 is 395.84 meters per minute.